probability of full surround probabilities and misdetection probabilities, we show them as a function of your sensing time. If you have collaboration between users to find a certain primary user, what would happen is these probabilities would change in value because you have a collaborative decision. So this model can be extended, or here I'm talking by this model, I'm talking about the first and second part of the work, because this part of the work, collaboration wouldn't really matter.
I think the question was different, right? Because if you are doing the traffic estimation, you assume that there is only primary user. What if there are other secondary users on the channel that are, it's like peer-to-peer, right? So when you are estimating the traffic, you're not estimating only traffic on the primary user, but everyone else.
Oh, that are
other secondary users trying to get in an uncoordinated fashion.
Well, because the math is extremely hard, so in this part we're assuming that whoever user is using this channel has a stationary distribution for a period of time. By period of time, I'm talking about the period of time during which you're observing the channel. So here we're talking about if your observation window is, I mean, you can assume that the probability distribution, the probability is stationary, the traffic is stationary, so this would apply.
I see.
Yeah.
But this is right.
No, but I mean, first, actually, one way to think of it is what Daniel just said. Suppose that you're just being nice to the primary. So the secondary user pair, when they get in, they become kind of primary user. And, well, you have to assume that the distribution.
But it changes the distribution.
No, but assume that all the same have the same distributions. So now there is the secondary pair trying to get in, and well, it changes traffic level. So I was wondering.
Yeah.
Of course, the more users, secondary users that are competing, the more difficult it will be. But then probably, then you may have to.
Yeah, but he's trying to find the channel that has the least occupancy. So still, it will work.
Still, no, it will work. It will work. But I wonder whether the number of stages would depend on the actual traffic in the system. So if you know there are a few users, maybe you. Anyway,
so the thing
it's a different problem.
It's a different problem because if you're always looking for the channels that have the least occupancy, and then you have many users who are looking for the channels that have least occupancy, and you end up with a uniform distribution in occupancy, and so that channel knowledge doesn't help anymore. That would be asymptotic.
The other question is, like, he can actually filter out, like, if he uses some smarter sensing techniques, he can recognize primary versus secondary. So with secondary, he can collide. Like if the channel is occupied only by secondary users, right? Then he can go with collisions if he, be more aggressive. We haven't really explored that, but it could be that.
But yeah.
So then if secondary user is next, then all the other secondary users will stop fighting for their channel.
Right.
Right.
Or at least there's some coordination from the secondary user traffic. Yeah.
So yeah, now we're assuming that there is one channel, and you're trying to estimate there's a primary user using the channel. The traffic statistics are stationary, and the on and off times are exponentially distributed. And what would be the error in estimating the traffic parameters? So I'll first start talking about the Dury cycle. And I'll start with a very simple case of you have uniform sample stream, and you are just doing averaging, which is the most intuitive and simplest estimator. And first, I will assume that you have perfect spectrum sensing. So basically, what you do, you take samples at this that are with equal intersample periods, and the goal here is to calculate the error in the estimate. So you have 2 to the n possible outcomes, and you want to calculate the error. You have to do an expectation over all 2 to the n streams. And in this expectation, the probability is basically the probability of seeing having a certain stream of these 2 to the n streams. And the probability of the outcome comes from this function, which is a function of your transition probability. And if you calculate this expected value, you get the mean squared error in your estimate, and we derived it to be equal to this expression here. So the first part of the expression, this is basically normalized variance of a binomial distribution. So this is if these samples are IID, this is the variance that you would get. But because the on and off times are exponentially distributed, there's correlation between the samples. And that's why you end up with this added term. And to look at the more practical cases, we consider the case where you have too many samples for a very long observation window. So if you take the limit as the number of samples go to infinity, as the observation window goes to infinity, you will see that the part due to correlation disappears. But on the other hand, if you take the limit as the number of samples goes to infinity while your observation window is fixed, what happens is you hit a lower bound, and this is caused by the correlation between the samples. Now to look at a more complicated case where you have spectrum sensing errors. So the sample stream that you get, not all of the readings are correct. There's a probability of false alarm and a probability of misdetection. The first problem is because of the spectrum sensing errors, you end up with the estimator, the averaging estimator being biased. So if you calculate the expected value, it's given by this expression. So we propose this unbiased estimator, we basically remove the bias, and we calculated the same expectation from the first slide over all 2 to the n samples. But then note in this case, the probability of seeing a certain outcome is much more complicated because you have to put into consideration that any stream can lead to any other stream with a non-zero probability because of false alarms and misdetection probabilities. If you take this expectation, you end up with this expression for the error in the mean squared error in your estimate. So this part is basically like the part from assuming perfect sensing, but you have this added part over here which accounts for the error in your estimate caused by the spectrum sensing errors. And again, if you take the limits t goes to infinity, you will see that this part is still there. And this is because we assumed, which is a typical assumption, that the spectrum sensing errors are IID. So if you increase your window to infinity, it doesn't matter, you will still have the same error caused by the spectrum sensing errors. However, if you take the limit as n goes to infinity for a certain window, the error caused by sensing would disappear, and you end up like the case with perfect sensing. Then we looked at a more practical case where in algorithms, I mean, here we did an assumption that you have uniform sampling. But in actual algorithms, people usually look into non-uniform sampling. You have random samples taken at random periods of time. And again, we calculated the mean squared error in the estimate, and it is given by this expression over here. Again, this part is variance of binomial distribution, and this part accounts for the correlation between the samples. And we derive the expression, if you have sensing errors, spectrum sensing errors, you end up with the same added term as well. And again, here we remove the bias as well. So as you can see, the error is a function of t, where t is, or tk, where tks are the intersample periods. So we found it interesting to look at if you are sampling your channel in a non-uniform way, there obviously looks like there might be a certain way to sample this channel to minimize your sensing error. So in this part, we basically it's a convex optimization problem. We proved it to be convex, and basically you want to minimize the mean squared error under the constraint that the total sensing window is given by t. We solved this by Lagrangian duality, and the results are basically given in this expressions over here. The expressions don't really tell much, so that's why I have a simple animation. I'll give you a briefing of or how this works, how the solution looks like. So if you have a certain observation window, you'll find that the optimal way of distributing these samples is basically uniform for the middle samples, but for the samples on the edges, it's non-uniform. They're equal and they're smaller than the rest of the intersample periods. And as you decrease this observation window, these two samples come closer to one another until they actually coincide in time, meaning that you are weighting the sample at the edge. So this is what happens when you decrease your J3 for some reason. So here I will be decreasing the observation window, and as you can see, the samples at the edges come closer till they actually coincide in time, and then the other samples at the edges come closer till they coincide in time, and so on. And I must say the problem, okay, first of all, this is the expression for the error, the mean squared error in the estimate. And I must say that this expression is just a lower bound on your error. It cannot really be reached in practical cases because in order to calculate these times, it's a function of u, the very same parameter you're trying to estimate. So these serve as lower bounds. The fact that you get, I mean, for the optimal stream, the optimal way of sampling the stream, you get samples coinciding in time, imply that weighting these samples might get you a better, a more accurate estimate. So that's why, as an offshoot of this work, we also looked at the case where you have uniform sampling, but you have weighted stream averaging. So I didn't do the math for this part. It was Chunhao, the fellow PhD student at our lab. So I'm including the slide because the result I will refer to this result later in this presentation. So what Chunhao did is the estimator is basically the samples are weighted. The summation of the weights is 1 so that your estimator would be unbiased. And he found out that there's an optimal weighting sequence, and surprisingly, this weighting sequence is the same for all samples except for the samples at the edges, which is a little bit similar in some way to the non-uniform sampling case. He derived the expressions for the error under this optimal weighting sequence, and the error as n goes to infinity. And I will refer to these expressions later. And as you can see, still you have a lower bound caused by sample correlation. Now, if you want to talk about the accuracy of an estimator, the best metric there is, or the best measure would be the Kramer-Rao bound. Kramer-Rao bound, it's basically it's the lower bound on the accuracy of any unbiased estimator, and usually it's the math behind it is a bit complicated. It's basically the idea is you have a likelihood function, and the Kramer-Rao bound is given by the inverse of the Fisher information. So it's this expression over here. You take the expectation for all 2 to the n possible streams of the derivative of the log of the likelihood function. So we derive the expression for estimating u. In this part, we're assuming that there is knowledge of lambda f, and we will drop this assumption later. The expression is quite bulky. This is the denominator. Doesn't tell much, so we take the limit to make it look more useful. If you take the limit as t goes to infinity, you end up with the binomial distribution, the variance of the binomial distribution again. If you take the limit of number of samples as it goes to infinity, you come up with this expression here. If you compare this expression with the expression for weighted sampling that Chunhao derived, you'll find out it's exactly the same expression, only the t, or the total observation window length, is decreased by a factor of